Hello everyone. So I would first like to thank the organizer for giving me this opportunity to come here and give this presentation. So and thank you Piali for introducing me. So I joined IISc Bangalore last year in May and it has been more than a year now. So I mostly work in computational modeling related to understand the sun's magnetic field and its impact on space weather. But the physics that we understand can be extended to other stars as well. So moving on, so this is the solar physics group at IISc. I have written down new because IISc has this long legacy of producing good solar physicists who mostly was working with Arnab Rai Chaudhuri. So now I have 3 PhD students. So Anuna is one of them. So they are like in their second year or first year. So Anuna is also here. She'll be presenting one poster. And I have one master student. So with this small group, I have started to understand the magnetic field in the sun. So should I continue? Yeah. So moving on, so today what I'm going to talk about is the sunspot cycle and like how we can do the prediction of sunspot cycle. Why that is important? We know that sun is our nearest star and most of the activities that happen in the sun affects the environment like the radiative, electromagnetic and particulate environment around the earth as well as in the heliosphere. So now one of the primary reason for solar activity or sunspot cycle is the sun's magnetic field, and one of the primary manifestation of sun's magnetic field happens to sunspots, which appears as these dark patches on the solar surface, and they are huge in size compared to the size of the earth, you can see, and they are magnetic in nature, and they are mostly appears as bipolar spots, like one positive polarity and on the negative polarity on the solar surface, and they are the source of high activity, for example, solar flares, coronal mass ejections, etc. Now, yeah. Yes. So as I was saying, so why sunspots are important, and if we look at the number of sunspots, how it varies over time. So it has a rough periodicity of 11 years, as you can see here. Although the number of, like what will be the number of sunspots during the solar maximum, that varies quite a lot from one cycle to the other. And why we're interested in sunspot number cycle, currently we are at solar cycle 25 at the peak. Previous cycle was cycle 24 and so on, if you go back in time. And the main reason that why we're interested to predict what should be the next cycle amplitude, or let's say, because all other solar activity, for example, starting from number of solar flares, coronal mass ejections, total solar irradiance, all they follow the same pattern at the sunspot number cycle. So in a way, if we can predict the number of sunspot that is going to be there in the next decade, we can overall say what will be the space environment in the next decade in around the earth as well as in the heliosphere. So that's the idea. So that is from the point of view of space weather or space climate prediction. But as a individually, particularly from theoretical point of view, you can still try to understand what generates this magnetic cycle in a star. Your understanding can be then applied to other stars as well. So that can even expand your view. So the advantage that we have in solar physics, we have lots of good resolution observational data, and the work that I'm going to discuss mostly is going to highlight the importance of understanding the observational data and incorporating in our simulations. So moving on, as I was saying, sunspot cycle prediction, it became quite a popular problem to solve starting from early, let's say 2006 or so. That was the beginning of solar cycle 24. But here, what I'm showing here on this plot is all are predicting what should be the cycle 24 solar maximum. And they use diverse kind of techniques starting from mathematical methods, nonlinear analysis, machine learning, physics-based model, all these things. And they all predicted different values. And the color is according to if there is a similarity in the prediction technique. But even if there are similarities in the prediction technique, you may think like the number they predict should be the same, but that is not the case. And what I have shown here in the dashed line is what was actually observed. So you can see how off it can be from the minimum value predicted and the maximum value predicted. So there is not only discrepancy between the different possible ways of predicting sunspot cycle, there are also discrepancies even if you keep the prediction method same. So that was 2006, 2007, around that time, in the beginning of solar cycle 24. So now the field has evolved, and now let's see what happened in the beginning of solar cycle 25, which was around 2019 or so. So then the picture didn't change that much actually. So still, what is this dashed line? What you can see here was the solar cycle 24 predicted value. And again, we can see the diverse range of predictions. Also, some people use the same method, some people use the different kinds of methods, but still there is no similarities or convergence in the prediction. So there are lots of things to do. What I'll be mostly focusing on today here is the physics-based prediction. So where we know that the laws of magnetohydrodynamics is valid in the sun, and if we can use those, how we can improve our prediction. So during cycle 24 prediction, that was around 20 years ago. So there were only two physics-based predictions. So these two, and it was in 2007, 2006, as I mentioned. And now for cycle 25, there are more physics-based predictions. So all of these, in a way, incorporated the fact that the origin and the evolution of magnetic field in the sun is dictated by the solar dynamo or the dynamo mechanism. But even if they both use the dynamo simulations during cycle 24 prediction, we can see the discrepancy between just the two physics-based prediction. But one predicted this should be the value of cycle 24, which matched very well with the observation, and the other predicted it to be quite large. So same method gave different result. Now move on to the next decade, cycle 25 prediction. Now we see a much more convergence between different simulations or different physics-based predictions. So my talk will be to in a way highlight what changed between this one decade, like how as a community we improved our understanding. So as I'll be talking about the physics-based prediction, so let's look at this very basic mechanism or the cross-section of the sun. We know this is core is the source of the energy. Beyond that, we have radiative zone, then we have convection zone, and on the surface, we have photosphere, where we see the sunspots being emerged. Now, the generation and the evolution of magnetic field mostly happens in the solar convection zone, where we know there is an energy exchange between the magnetic field and the velocity field that happens through the laws of magnetohydrodynamics. And the particular equation that mostly we solve in case of sun's magnetic field generation is known as the magnetic induction equation. So this B is the magnetic field, V is the velocity field, eta is magnetic diffusivity. V here is the plasma velocity, which in general for the sun we know quite well from the observational perspective. So what we do using the observed velocity field, we try to see whether we can regenerate the magnetic field, which will again match with the observed magnetic field. So if we can do that accurately, so then in a way we can capture the solar cycle variation by solving this magnetic induction equation. So the way of doing it, I'll not go into the details. So we can break the sun's magnetic field into two components. One is the toroidal and the poloidal component. Toroidal is the component which is along the azimuthal direction. Poloidal is one which is in the earth theta plane or the meridional plane. So the generation from toroidal to poloidal, that happens through Backward-Clinton mechanism, and as well as there are other existing mechanisms which tells us how this can be generated. And the other mechanism, poloidal to toroidal, happens through omega effect. Again, I'll talk very briefly about these methods because it will show us the importance of using observational data. So what happens in the solar convection zone, these two components interchange between themselves in a 11-year cycle, and that generates this well-known decadal scale variation in the sun's magnetic field. Now this conversion or this generation can act very well because we know that within the solar convection zone or in the sun, most of the astrophysical property is the Alfvén's flux freezing theorem is valid. And depending on the local plasma beta values, we can see how this velocity field can generate the magnetic field. So moving on, the generation of the toroidal field happens through the differential rotation. We know that the sun's equator rotates faster than the poles, and that it, in fact, can in a way generate one component which was originally in the earth theta plane and make it as a phi directional component or the toroidal component. Now, once this generation and amplification of the toroidal components becomes strong enough, what happens? Magnetic buoyancy kicks in, and the magnetic field from the base of the solar convection zone or at the depth of the solar convection zone starts rising on the solar surface and appears as bipolar spot. So all these mechanisms are happening within the solar convection zone. And on the surface, what you see is this pair of sunspots with a certain tilt. So this is a positive polarity and the negative polarity. And the pattern exactly becomes opposite in the other hemisphere. And this pattern with this certain tilt is very important for the sustenance of sunspot cycle or how the dynamo works. So this is a simulation that is showing that on the solar surface, because again there is large scale velocity field as well as diffusion. So this magnetic field from the leading polarities, we call them leading polarities based on the rotation. So they cancels out between each other, and the flux from the following polarities that goes towards the pole and alters this global dipolar field. And that is what happens on the solar surface, and it is observationally verified as well. And what we in general do is solve the magnetic induction equation on the solar surface given the velocity field and the diffusion. And this is what we observe as well. And the computational model that do that is known as a surface flux transport model. So, and this particular image is again taken from observational data. So I'll just highlight, you can see this butterfly like wings, and this is famously known as Swan's magnetic butterfly diagram. And again, this flux cancellation between leading polarities and the flux traversing from the following polarities and going to the pole, that roughly you can see. And this patterns repeats itself from one solar cycle to the other, just with the change of magnetic field. Now moving on, so if we want to do solar cycle prediction, which are the main key point we should look at? One is, if we want to do how the solar dynamo works, as I said, the conversion between poloidal to toroidal. So what we have to do, we have to guess what is the poloidal field at a sunspot cycle minimum, because that will generate the toroidal field in the following cycle, and that is in a way going to represent how strong or weak the solar cycle going to be. So there is a strong correlation between the dipole moment at sunspot minimum, or the amplitude of dipole moment, and the following cycle amplitude. So if one group of scientists, they want to do solar cycle prediction, they try to focus using physics-based model or precursor-based model. They try to generate or get an idea of what should be the dipole moment at minimum. And this is what mostly the physics model will look at. Now again, what we do on the solar surface, because dipole moment is getting generated, you can easily see it on the solar surface. So we solve again magnetic induction equation on the solar surface given the observed velocity field and diffusivity with emergence of new sunspots. Okay, that is something that we do. This new sunspot will be motivated by observational data, so that we shouldn't miss. And this S, or this source term, becomes very important. How accurately you model this source term given your observational sunspot properties will dictate how accurate you can predict the or do prediction for solar sunspot cycles. So I'll be mostly talking about one particular simulations or the computational model that I developed with Dibendu, my PhD supervisor. So what we did, we took the observational data from different observatories, and we incorporated as much physics possible from observation, so that our data assimilation become accurate as well as in conjecture with the observation. And doing that, what we performed is one century scale simulation starting from 1915. So the main objective here was to validate our simulation for the maximum amount of range, so that once we can match our simulation generated result with older observation, we can claim that the model that we have developed or the physics that we are using should be valid enough for doing solar cycle prediction. So this century scale simulation helped us in doing validation of the model. We could also calibrate the model with accurate combination of the parameter space, so that we can finally claim that whatever we are predicting should be trusted enough. And this is what you are seeing from the simulation. So again, you can see the sunspot pairs appearing and the flux cancellation is going on. And of course, the kind of expected magnetic butterfly diagram that matched with the observation. But to be more quantitatively saying how well we did by comparing with the observation. So what we can see at the top panel is again sunspot associated flux. So this went as the source term in our simulation taken from observation. And this is the polar field, or you can in a way say the dipole moment that we generated from our simulation. So what you are seeing here again with the error bar, it is the observation, and with the solid lines, it is the simulated magnetic flux in North Pole in blue, and in red, it is in South Pole. Again, if we are focusing mostly during the solar minimum, because if you remember, that was our focus. We want to do the prediction sitting or knowing what is the dipole moment strength at the solar minimum. So if we can match it well during the solar minimum, then we can use our idea for solar cycle prediction. And that we did for last 7 or 8 solar cycle, and the correlation between the observed and simulated polar field came out to be quite satisfactory, 0.88. So in a way, we could capture what was happening on the solar surface very well while we are doing this data assimilation simulations. Once we have done it, so the next stage is how now we can do the prediction. Because what we got is in a way the evolution of the poloidal field. Now we want to know what should be the toroidal field coming from this poloidal field so that we can do the prediction of sunspot cycle. And again, I'll not go into the technical details. So we came up with, and also this technique was not very new to the topic. So what we did is like at every solar minimum, we utilize the poloidal field that was generated from our surface flux transport model. We assimilated it into an existing dynamo model and then simulated it to get the next toroidal field. And if you want to see like after the SFT or the poloidal field assimilation, so the dynamo input should change from here to there. So you can see a clear difference like how the data assimilation can change the dynamo toroidal field beginning. So we can expect that if our data assimilation is correct, it should be reflected in the toroidal field generation as well as the following cycle amplitude. And we did that at every solar minimum starting from 17 to 24. What you are seeing here in this gray line as well as this solid black line is the magnetic flux associated with the sunspot. So this is purely observation. And after doing this data assimilation, this magenta curve is showing what we got from this combination of SFT and dynamo model. And again, you can see very nicely for most of the cycles, the pink amplitude matched quite well. Although there are certain discrepancy between the solar minimum phase, but again, I mean, using it, changing a different model parameter, we resolved it. If someone is interested, I can focus on the minimum. But for solar cycle prediction, the maximum match was meant the most. And if we did a correlation analysis between the assimilated SFT plus dynamo prediction, it matched quite well with the observation with a 0.87 correlation coefficient. So this technique of poloidal field generation using an observational data driven simulation and then combining it to a dynamo model worked very well for last 8 solar cycles. So the next objective was to let's do a prediction for cycle 25. So we did this prediction when it was before cycle 25 started in 2019. So it was around 2017 or so. And then we considered different kind of possibilities that can happen even during those last 2 years. And we presented one ensemble average or ensemble prediction for cycle 25. So you can see the maximum and the minimum that came from our 100 ensemble runs. And in between, the magenta one is showing the mean. So if people are interested to know the exact value that we predicted, so we said the range should be between 109 to 139. For cycle 24, it was around 108, 113 or so. So in a way, cycle 25 would be roughly almost similar, a bit slightly stronger for cycle 24. So that was more or less the result. Now, again, I'm coming back to this picture. So in this range of simulations, so this is where our prediction stood. And we are not the only group doing such predictions using physics-based models. So there are other groups. And still, we can see this striking change in pattern where all these groups are coming or converging towards a similarish value for cycle 25. So of course, all of them either considered a very good model for the surface magnetic field evolution, which mimicked the poloidal field generation, or they used a dynamo simulation or a precursor made method. So now what changed, as I said, the careful assimilation of observation. Now the question you may ask, like, okay, we have now spent 10 years or a decade between this to this. Now, does that mean that now we have solved the solar cycle prediction problem and then this will be like a solved solution? So this is where cycle 25 maxima stands here now. So still, although there are these convergence among different predictions using more or less the same physics, still we are not perfectly solved the problem. So there is still scopes of doing like future improvement to the simulation. So I'll end my talk with mostly saying what could be the source of these uncertainties in our prediction. one thing that we must remember that sun is after all a turbulent body. So your prediction range or how much you can predict, that should be always limited to the thing that, okay, it's a turbulent system and you cannot do predictions for infinitely. In fact, it has been shown that you can do such predictions only up to a solar cycle or so. So even if you understand more or less the overall physics of the sun, that it follows the MHD laws, it doesn't mean that, okay, we can do prediction for next 20 solar cycles or so. Your prediction can be only up to one solar cycle. And then the question is like, okay, we are claiming that, okay, we now understand the origin or the laws of physics within the sun, that how the dynamo works. But actually there are many uncertainties about the dynamo. So I talked about one kind of dynamo, which on the surface level was motivated by the observational data. But there exist other contemporary theories, for example, mean field dynamos, small scale versus large scale dynamos, location of the toroidal field generation, and etc. Now, of course, as I mentioned already about the stochastic nature of the turbulent medium of the solar convection zone, and that gives rise to various kinds of uncertainties, which acts as a source term in most all simulations. And of course, we shouldn't forget about the nonlinear effects, which is again observationally verified. And I mentioned about the short memory. So in a way, I'll conclude with this slide that, of course, we have performed this century scale simulation and shown that, look at how much we can push our simulations to match with observation, but there are sources of uncertainties. However, the observation that we saw on the solar surface, we can more or less say with conviction that that in a way mostly regulated the sunspot cycle variation that we saw in the last 100 years. But there are fields of improvement which can make it more accurate, and I think like as a community we are also working on it. Yeah, so I'll end my talk here. Thank you.
Okay, thank you, Prantika, for a very nice talk. And I also realized that both me and Prantika predicted solar cycles for our PhDs. And not only that, our predictions were published one solar cycle apart.
Yes.
And both were correct.
Yes, more or less.
Yeah. Okay, so maybe we can have some questions.
Prantika, thanks for the nice talk. In the first slide that you showed, it was the number of sunspot versus the year.
Mhm.
Is there a overlapping sinusoidal on top of it, or am I just
Okay,
imagining?
yeah. So yes, I mean, so sunspot cycle, this decadal scale sunspot cycle is not the only cycle that you observe. If you are looking at much longer scale data, there are other cycles. The periodicity can be like 70 years or so. There are certain other cycles where the periodicity can be 200 years or so. It depends on the what time scale you are looking at. So we were interested in sunspot cycle particularly because of its application to space weather or space climate. But there are other cycles as well.
Yeah, according to your model, did you also predict the 1920 minima, which was which was abnormally a long minima?
1920.
2019 and 2020 minima.
Okay, no. So
because it was a very, very long minima, very abnormal minima.
I would say so. Compare any solar minimum, you will see that. But I would say if I just go back to the observation, the long minima actually you probably was more observed during this phase, which was the end of cycle 23. So it started in 2007. Yeah, understood. You said like this one. Between 24-25, so that was actually to our standard compared to the other cycles was not that long. It was quite standard. I understood. That is the expected solar minimum phase that we should expect for by the end of a decadal scale cycle. This 1 year inactive phase, it is a standard expectation whenever one solar cycle ends. But compared to that, that is, that minimum should be always there. I mean, that 1 year low activity phase happened in every other cycle end. But during solar cycle 23, the minimum extended to 2.5 years or so.
That minima was more abnormal.
Yes.
13 minima
Not
was
this one. No, we didn't look at the solar minimum phase because as I was saying, like solar cycle prediction looks more about the space weather impact. Like if there are many sunspots, so there will be many more solar flares and coronal mass ejections. The minimum phase, people are less interested about its like broader application you can think about.
Yeah.
Hello, thank you
Yes.
for the nice talk. So the place where we were describing the source function for the sunspots, so you are taking the source function as a from observations, right? So my question is, are there any dynamo models or physically motivated dynamo models which naturally give up the like gives rise to the source function?
Okay, so for example, so ideally what you would want a full MHD model which will not only solve whatever is happening in the interior, but also will show where exactly the sunspots are emerging. But there is no existing MHD full sun simulation which does that. But there are models which will only focus on, let's say, the emergence of individual sunspots, or let's say group of sunspots, but at what exact latitude, longitude, position they are going to appear, because that will also depend on its impact on the poloidal field generation. Such accurate models do not exist. And again, because sun is after all a stochastic system, you cannot do that either. But certain approximations you can definitely do.
Yeah, if you solve it, $1 million is yours. It's a grand challenge for me. Yeah. So we don't have any more questions. So let us thank Prantika and all the other speakers of this session.